In the last video we talked about the non-inverting amplifier. In this video we are going to talk about the inverting amplifier. We'll start by looking again at the non-inverting amplifier as a starting point. Standard op-amp diagram with power supplies. One output, two inputs. The non-inverting input, the inverting input, and for the non-inverting amplifier we had a voltage divider in the feedback loop. So that is a non-inverting amplifier. Let's put some values for these resistors. So a quick review on how this works. If we put a voltage here, let's say just for example 2 volts, the output will be made to whatever it takes to make the two input voltages equal. So we're going to assume that this will also be 2 volts. Let's make these positive so we know what we are doing. So with equal resistors in the feedback, we would get a gain of 2, so the output would be 4 volts. And let's double check that. So the output will be whatever it takes to make the two input voltages equal. We will have 0 volts here. We will gain 2 volts because from 0 volts to plus 2. And since these two resistors in the series circuit are equal, the voltage across them must be equal. So if we gain 2 volts, we gain 2 more to get plus 4 volts, and we see that the circuit does exactly what we expect. Now let's convert this into an inverting amplifier by simply swapping where the input and the ground are. Now we have an inverting amplifier. Let's see how it works. In this case, we have the non-inverting input grounded, so that will always be 0 volts. And the output will be whatever it takes to balance that, making the inverting input 0 volts also. This is often referred to as a virtual ground. I'm a little uncomfortable with that definition because, as we know, the definition of a ground is the point where you measure all your voltages from, so that will always be 0 volts, and a ground must also be able to receive or deliver high currents without that voltage changing. And there is no current flowing into this op-amp, so that means that this really isn't like a ground. But then again it is, because any current that flows into here will eventually flow into the output of the op-amp, or vice versa. Any current that flows out of here will come from the op-amp output. So in a way it does act like a ground. So okay, I will concede to that and call that a virtual ground. So let's see what happens when we put an input voltage here. Let's put plus 2 volts here, and the output will be whatever it takes to keep the two inputs equal. So this output voltage will be whatever it takes to make that 0 volts. So we start with plus 2 volts and we lose 2 volts to get to ground. So we start at plus 2, we lose 2 volts. And since these two resistors are equal, we must lose the same amount of voltage across each one. So we lose 2 volts. We can't gain because we're in a series circuit, so whichever way the current is flowing, in this case the current will be flowing in this direction. The conventional current will be flowing in this direction. And so if we lose voltage, we'll continue to lose voltage because we lose voltage when we go in the direction of conventional current. So we lose 2 volts to get to 0, lose 2 more to get us to minus 2 volts. So the output is going to be minus 2 volts. So the voltage that will cause this to be 0 will be minus 2. So plus 2 here, minus 2 there. Notice that with the two resistors being equal in the feedback, that we get a gain of 1. So the formula for this circuit is our voltage gain is equal to minus, let's put some numbers here, R2 and R1, equals minus R 2 over R1. The minus sign simply reminds us that our polarity will always be opposite from the input. The output polarity will always be opposite from the input polarity. So notice we have plus 2 here, we have minus 2 there. So for those of you who like formulas, there's the formula for it. The output will be simply the ratio of these two resistors, but the polarity gets reversed. So let's see what happens if we put a negative voltage over here. Let's put minus 3.5 volts. Erase these numbers and see what happens. Okay, so we go from, I wanted to make that minus. Let's try that again. So we have minus 3.5 volts here. We gain that 3.5 volts to get to 0. So we go from minus 3.5 to 0. We've gained 3.5 volts. The two resistors are equal, so the voltages will be equal. 3.5 volts here. So we gain 3.5 volts to get up to 0. We have to continue the gain. Now the conventional current is flowing this direction. So as we go against the conventional current, we will gain voltage. So we gain 3.5. We gain 3.5 more, so minus 3.5 to 0. Another 3.5 takes us to plus 3.5 volts. So the output is plus 3.5 volts. So once again, with the two resistors being equal, our gain is going to be equal to 1. Now let's change this resistor and make it twice the other resistor to 20K and see what happens. Nothing changes over here. This is still minus 3.5 volts. This is still 0. So we gain 3.5 volts. But now, since we have twice the resistance, we must have twice the voltage. So this is going to be 7 volts. So minus 3.5 to 0. Then we gain 7 volts. That means this will be plus 7. So our output will be plus 7 volts. So let's look at these resistors. We have a 2-to-1 ratio. We should have a gain of 2, or technically a gain of minus 2, because once again we reverse our polarity. So is 7 volts twice 3.5 volts? Yes, it is. So we have a gain of 2, but the polarity gets reversed. So once again, for a quick review, the inverting amplifier looks a lot like the non-inverting amplifier, except we swap the ground and the input. So our non-inverting input is always grounded on the inverting amplifier. That means that the voltage at the inverting input, assuming everything is balanced, should be 0 volts. And the gain will be the ratio of these two resistors with the polarity changed. Now let's take this a step further. Let's make this 30K. So now we have a gain of 3. A 3-to-1 ratio, we should have a gain of 3. Let's see if this works out. So minus 3.5 volts here, and we should have 10.5 volts across there. So we gain 3.5 volts to get to 0, gain 10.5 more, so this should be plus 10.5 volts, making the output plus 10.5 volts. But you've probably already noticed that's impossible because we cannot reach that voltage. So our output is going to be roughly, in this case, plus 9.5 volts. So let's see what we actually have at this inverting input and see how this circuit balances out. We have 9.5 volts at the output, minus 3.5 volts at the input. That gives us a total voltage across the voltage divider of 9.5 plus 3.5, which gives us a total of 13 volts. Since we have a 3-to-1 ratio of the resistance, we divide that by 4, and that gives us the voltage across this resistor, which will be 3.25 volts. So now we're going from 3.5 and we are gaining 3.25, so this is going to be 0.25 volts. So we no longer have the circuit balanced. I've come across engineers who didn't have much experience who would take a look at this circuit and immediately tell me, change that op amp. The op amp is bad. because they have been trained that if these two voltages are not equal, that the op-amp is bad. But we can see that this op-amp is doing exactly what it should be doing, and that the circuit is simply out of balance. What can we do to solve the problem? Well, same things we could with the non-inverting amplifier. We could limit our input. If we have a lower input voltage, then we'll have a lower output voltage. So just say, well, the input's too high, we're overdriving it. The circuit doesn't change, we're just outside the parameters. We could lower the gain by keeping the resistor ratio lower, and then we could accept this voltage, but we'd have a lower output voltage, but we would have a acceptable, usable circuit. And last but not least, and sometimes the more logical thing to do, is simply increase the supply voltage Slight redesign of the circuit. Now this can reach 10.5 volts. This will balance out to 0 volts, and we will have a properly working inverting amplifier. In our next video, we'll take a look at the next step, which is the differential amplifier.